All right, good morning, everybody. So today we are going to look at chapter 20, and then there's just the two parts to the video there. So tomorrow we'll actually not have any new video, but you can just, we'll just spend some time on synthesis problems. If there's any other problems that you want to discuss, we can go over certainly any of those, but I'll have a couple of synthesis problems ready so that we can work on some of those. Seems like that is an area that students like to have extra work done on. All right, so the week homework 3 is up, and then labs 5 and 6 are up. One is due on the 11th, which I think is Saturday, and then the other one is due on Monday, the 13th. And then quiz 2 is available tomorrow, and that will be due on Friday by 11:59 p.m. Questions on any announcement stuff? All right, so we're going to start, I think, today with some nomenclature. We haven't seen that a whole lot, or not in a while anyways. So when we're naming aldehydes, the aldehyde again and the ketone both have carbonyl groups, which is the C double bond O, and that is common to several different functional groups. The aldehyde has the H on one side, and the ketone has an R on one side. So that is the difference between a ketone and an aldehyde, is that the aldehyde has that hydrogen on the other side of the carbonyl, and the ketone has a carbon group. In a ketone, the R groups do not have to be the same. They can be different. So that's these right there. Those can be different versus the aldehyde, which has the H. When we name an aldehyde, you find the longest carbon chain, which has to include the aldehyde. And then the aldehyde carbon is number 1. That's always going to be 1. Aldehydes cannot be in a ring. And when you are naming the aldehyde, you drop the E of like pentane, and then you end it with al. So this structure ends up being 3-bromo-2-ethyl pentanal. And then for naming ketones, you have the longest carbon chain, which contains the ketone, and you want this carbonyl carbon to get the lowest numbering. So this one would be 3. This is 4,4-dimethyl-3-heptanone. Carbonyls can be in a ring, so if you had this right here, this is cyclohexanone. So cyclohexane is the parent, it has a ketone, and it's cyclohexanone, we assume that it is at 1. So if the carbonyl is in the ring, this is at carbon 1. All right, questions there on the naming? Other things that we'll look at here is that our carbonyl carbon is going to act as an electrophile, and that is due to resonance. So if we drew the electrons onto the oxygen, that makes this carbon positive, which makes it a good electrophile. There's also induction, and sterically it's a good place to attack, so that makes it a good electrophile. So we're going to see a lot of different electrophilic attacks on carbonyls in this chapter. Questions there? All right, what is the IUPAC name for this structure here? Okay, so most of you are indicating B as the answer. So this one is an aldehyde. So it should end in the al. And 6 carbons, we have hexanal, and then we're just going to list alphabetically. The ethyl is at 2 because our hexanal carbon has to be at 1, so B is the correct answer here. Very good. Questions on this one? All right, how about this one? Okay, good. So most of you guessed A, and we have a cyclic structure. So our ketone is at carbon 1. And this is 6 carbons, and so it's cyclohexanone. The alcohol group is treated as a hydroxy. And then we have methyl groups. So this will be 4-hydroxy, alphabetically wise. H comes before M. 2,2-dimethyl cyclohexanone. So A is the correct answer there. Questions on this one? All right, next we're going to do our reactions. And I'm on functional group transformation page, page number 9. And a lot of the reactions that we did in chapter 20, we also saw in chapter 13 with the alcohols, those like the reduction of carbonyls. So I'm not going to re-add those to the book because they're already in there, but just be aware that some of these reactions may be in chapter 13. So this is from 20. First we have an aldehyde or ketone. We're going to add an alcohol to that. In the presence of catalytic acid. And what you can think of is this oxygen here of the carbonyl. You can draw a line down there and kind of fork split it open. And then you're going to add an OR double prime from the alcohol to each side of that. This is an acetal. And this is used as a protecting group. You can only use acetals on aldehydes and ketones. So this will not work on a carboxylic acid or an ester. To remove the S or acetal, you just add water and catalytic acid. And that will reform the carbonyl. And you'll be able to see that product in your lab if you haven't done it already. questions on either of those two reactions? So that acetal is used as a protecting group. So if you needed to do a reaction with where you're only reacting with an ester as opposed to the carbonyl, then you can protect that carbonyl. And we'll see a couple of examples of those today. If you add an amine, a primary amine, to a ketone or aldehyde, you're going to form an imine, and what's going to happen is the nitrogen is going to take the place of the oxygen, and then the R group comes along, as does, nope, just the R group comes along. There's nothing there. Just it should be N double bond to carbon and then the R prime. So those hydrogens will get picked up in proton transfers. So a primary amine plus a carbonyl gives you an imine. If you do the same reaction with a secondary amine, so there's two of these R groups. The N will still take the place of the oxygen. Both R's come along, and then we're going to form an enamine. The ene for the double bond, and the amine for the nitrogen. So secondary amine plus carbonyl gives you an enamine. All right, questions on that one? If you wanted to employ a different protecting group rather than the acetals, we can make a thioacetal. Oops. So the sulfurs will act just like the oxygen, and we form the thioacetal. These are nicer to use if you're working on a different part of your molecule and there is acid and water present. With the regular acetals, if you do that reaction in the presence of acid and water, you will deprotect your carbonyl, but these thioacetals require different reagents in order to remove them. Or they're a little bit sturdier. This also requires water and acid to remove it, but they're not as labile as the other ones. Questions on that. And then when we get to a later reaction page, we'll see there's a way to reduce this so that we just get the alkane back. Alright, another reaction that we're going to add to this page is not exactly carbonyl related, but it is a way to convert an alkyl halide into an ylide. using triphenylphosphine, followed by N-butyllithium, which is a base that has 4 carbons, which is the butyl. N means it's a straight chain carbon. And then the last carbon that's is ionically bonded to lithium. So there's a C minus and then the Li plus. And when you add triphenylphosphine, that's going to substitute and replace the halogen, and the base is going to make our carbon negative. So we'll have the negative carbon here and the positive here. And you may also see it drawn as our double bond PPH3. And this is called an ylide, which is used in the Wittig reaction. And we'll see that carbon-carbon bond forming reaction in a second here. Did you finish sewing?
Nope.
Or cutting out yours, twin?
I'm done cutting out the string.
Oh, do you need to tie it or not?
But not the twin. Because I might like it. Today Beer's getting little sibling. Baby Beer. No, little baby. Yeah. Little Beer is going to look more like a baby.
Alright, so this is the carbon-carbon bond forming page, which is page 14. I'm going to add potassium nitrile, and that's going to form a cyanohydrin. So that Cn minus is going to attack the carbonyl. So you add that carbon, or that nitrile group. This is a cyanohydrin. So that is a way to add a carbon. And when we get to the reduction page, we can see how to reduce that to an amine or to make it into the carboxylic acid. Alright, the next reaction on this page is the ylide. So we add the R double prime, and then there's a C that is double bonded to the Wittig reagent. And that C can be written as a C minus and the positive P. It's the same representation. And what you end up doing is replacing that oxygen with the C to the R prime. This is the Wittig reaction. Alright, questions on either of those two? So 2 new ways to form carbon. The first one also adds a nitrogen, and the second one is a quick way of adding an alkene. Previously, otherwise, if you wanted to add a carbon with a double bond, you might have gone through an alkyne and then had to do a whole bunch of other manipulations. But now if we have that carbonyl there, we can just add a carbon-carbon bond directly. So we don't have to add something with a Br and then eliminate it. Alright, the next reactions will be on the oxidation page. This is page 18 in my book. So this is that cyanohydrin that you just made up here with the potassium nitrile. If you add this reaction under heated conditions with acid and water, so a lot of times you'll see H3O plus written as acid or for acid and water. What this is going to do is it's going to oxidize that nitrile, the CN, to the carboxylic acid. So I have this C to the O carbonyl to the OH. So it's going to make this nitrile right here into the carboxylic acid. All right, any questions on that one? So if you needed to add a carboxylic acid, you could do it that way pretty quickly. All right, the other reaction here involves a ketone. We use MCPBA. Or an RCO3H. And that is going to add an oxygen in between the carbonyl and an carbon. So if you think of, there's some Price Is Right game where you squeeze a number in between two things, this is what that oxygen is doing. And so you have the choice of inserting your oxygen between this carbonyl and the R prime, or this position over here. And this is the Baeyer-Villiger reaction. And the order in which things shift is, if there's an H, that will shift first, followed by a tertiary position. Secondary is tied with phenyl. Primary, and then a CH3. So at this position right here, this is a tertiary carbon, and let's say this is a secondary one. The tertiary one is more likely to have that oxygen inserted into it, which is right here, versus the secondary. Questions there? And last is the reduction page. That's page 19. In this one we have an imine. We add NH2, NH2. H plus, followed by potassium hydroxide. And that is going to get rid of that imine. So we just are left with hydrogens here. This is the Wolff-Kishner reduction. And then with that thioacetal that we made earlier, we add something called Raney nickel. And that also gets rid of the thioacetal. So we're just left here with H's. So we can use those carbonyls to do our reactions and then leave no trace behind. So it's just the alkane there. Questions on either of those two reactions? All right, we have one more to add, and I'm going to have to flip the page over for this one. And this is with that cyanohydrin that you made with carbonyl and HCN and KCN. If you add lithium aluminum hydride, which is the super powerful reducing reagent, that will reduce the nitrile to an amine. All right, questions on those reactions? Okay, so what is the major product here? If we have a ketone in the presence of an ester, we add ethanol plus catalytic acid. What product do we get? All right, so most of you are choosing C, which is the correct answer. So the acid and water are just going to give us our carbonyl back. So we're going to get C there. All right, questions on this one? Okay, so let's look at the ones that we haven't filled in yet from the CPA. So we started with the hemiacid or the acetal, sorry, and then deprotecting it. If we add the carbonyl with this is R2, so this is a secondary amine, we're going to get the enamine. The carbonyl ester over here will be left alone. And the enamine will form, where it can form the most stable double bond, which will be that one. All right, any questions on the enamine? So that one will first go through the imine where there's an N double bond, and then that will tautomerize to the enamine. All right, and then for the primary amine, that will just form the imine. So that carbon double bond oxygen is going to just be replaced with the nitrogen and then the ethyl group there. And then adding the Wolff-Kishner reagent, the NH2NH2, that's going to eliminate that nitrogen. So we should just have the alkane there. Questions there? Okay, so if we have methyl cyclohexanone and we add this peroxy acid, which is the same as RCO3H, what product will we get here? This reaction can also be done with MCPBA. All right, so you guys are on the right track. We're either choosing B or C for the answer. So this will often be a mistake where somebody sees the MCP-BA reagent and assumes epoxide, and so they might choose A, but that's not in the wheelhouse, and either is D. So now what we're looking at, you recognize that this is a Baeyer-Villiger reaction, and then it comes down to which side is going to shift. If I look on the right side of the carbonyl, this is a secondary carbon. This side is a tertiary, and the tertiary is going to move more quickly than the secondary will. So if that one shifts over, we're going to squeeze the oxygen into there. So the correct answer here is B. Any questions on that one? All right, true or false? Is this the product that is formed in this reaction? All right, so the majority of you said true. And this is, let's see, I have one. That is true. So in this reaction, this is the Wittig. What happens is the oxygen gets cut off and this whole group here, including that double bond, gets kind of plopped on top of there, and we get our carbon-carbon double bond forming there. Questions on that one? And what about this one? KCN with HCN followed by acid and heat. So this is a two-step process. What do we get here? All right, let's take a look at this one. KCN and HCN. KCN is our CN minus, which will first attack here. So we'll get the OH from the HCN with CN minus. So that's going to go there first. So it would go to A. That's your halfway partial credit part. And then when we add acid and heat, that's going to hydrolyze that nitrile to the carboxylic acid. So we should get C for the answer there. So in this reaction, we have an OH plus that addition of the carboxylic acid there. Any questions there? All right, and let's look at the rest of these. If we have this methyl cyclohexanone, we saw the addition of, so this is the partial here. This has the nitrile, and we did this one which I forgot to draw in. So this is the carboxylic acid with the OH. If we add lithium aluminum nitrile to that cyanohydrin, we get the amine. And then the methyl cyclohexanone with 2 CH3SHs. We're going to get a thioacetal. So SCH3. That extra hydrogen will get picked up in a proton transfer. And if we add Raney nickel to that thioacetal, we get just a methyl cyclohexane back. And then we saw the Wittig reaction there. All right, questions here before we move on to the book problems. All right, here we're looking at arrow pushing mechanisms. And this is about the point in the semester from the spring where all of the classes were put online. So I had students send in answers at that time, and I still had those around. So we can look at other students' answers and see if this lines up with what we're dealing with here. And so we have a carbonyl here. The first step the student has going to the tosic acid. So tosic acid is just another acid. This is a proton transfer. So they protonate that alcohol or that carbonyl. So we have a protonated carbonyl here. And then the next thing to happen is the nitrogen from the methylamine is going to do a nucleophilic attack on the carbonyl. And when that happens, the methyl, the N-methyl, and all of the stuff on it is going to attack there and forms a new bond. Everything comes along. That nitrogen is positive. And another proton transfer is done here. So the hydrogen from the nitrogen can go over to the alcohol, forming water. And the nitrogen has a lone pair, which can form a double bond. So in this case, nitrogen's kind of acting like the oxygen to reform that double bond or form a double bond. And then it kicks off water in the process. So we lose water here to form this imine with a positive charge. And then we can do another proton transfer. So this water that was in the reaction can pick up that hydrogen. And then you get the product that is shown there. All right, any questions here? Or if anybody's still writing the mechanism down, I can wait before we go to the next slide. There will be 0 mechanism questions on the quiz tomorrow. All right, in this one, we're looking at predicting products. We have a carbonyl plus an amine, a primary amine. And that's because there's only one carbon bonded to the nitrogen in this case here. So this is what a student sent in for an answer. We have an A option of true, B for false. So do you think that what the student sent in there on the answer is correct? Okay, so most of you are voting for B, which is false, and you would be correct in that. So we're not going to form an enamine with a primary amine. So this is not correct here. What we're going to do instead is you have your starting material. The oxygen is going to get replaced by the nitrogen, and then the groups that were on nitrogen come along. So we're actually just going to form the imine here. Questions on that one? Okay, so for the next reaction, we have an aldehyde and a primary amine on the same molecule. Do you think this is the correct answer? True or false? All right, we've got a split pool. So half of you are answering true, half are false. And what we're expecting here is to form, if you have an aldehyde plus a primary amine, we should get an imine, which here we just have an amine. So this is not correct here. If you were doing this reaction with an R group here plus an R prime NH2, we would expect this reaction right here with this R down here. And so if our nitrogen is in the molecule, this is going to replace that right there. This is not a mechanism arrow, but that's going to replace that. And so we're going to form a cyclic structure. And to find out how many things are in it, this is 2. So we'll have a 5-membered ring. The nitrogen will be here. I have 1, 2, 3, 4, and then 5. I have too many carbons. Okay. I started counting at the one next to it. So this is 1, 2, 3, 4, and then the nitrogen is 5. Okay, does anybody have questions on that one? So if your nucleophile and your electrophile are on the same molecule, you should expect a cyclic product there. Right, questions there? All right, this is another mechanism question, which there was no student submission for here. So we'll go through this mechanism. The first step in most of these carbonyl reactions is going to be a proton transfer. And protonating that carbonyl makes it much more reactive. And once you have that activated carbonyl, we have NH with 2 ethyl groups, which is our nucleophile, which is going to attack the carbonyl. All right, so we have a nucleophilic attack after our proton transfer. So we have our ethylamine, which is acting as the nucleophile that can attack here. So the nitrogen and everything that was on it also comes. So we have this positive charge here. And the goal of the reaction is to get rid of that alcohol. And alcohol is a bad leaving group. So what I can do is a proton transfer. So the hydrogen from that nitrogen can shift over to the alcohol. This is positively charged. I still have this nitrogen down here. And then the lone pair from the nitrogen can form a double bond and kick that off. I'm just going to flip the nitrogen up here. And in this step here, the nitrogen or the product doesn't want to have a positively charged nitrogen. So we can just pick up a proton from down here. The water in the reaction can do that. And it will bring these electrons up to here, and those can go on to the nitrogen to get that product. Questions on that mechanism? So proton transfer, nucleophilic attack, another proton transfer. We do loss of leaving group, and then a proton transfer. So these carbonyl reactions have a lot of different proton transfers. All right, what is the major product here? All right, so some of you voted for false. The majority of you did. And this is not the right answer. If we are to do this reaction, this is a two-step one. In the first step, we add the sulfur group. If both of your sulfur groups are within the same molecule, we're going to get a cyclic thioacetal. So one of the sulfurs comes over, this is the other sulfur. So you'll get this structure. So these two carbons here are from these two here. So if your sulfurs are connected, you're going to get a cyclic thioacetal. And then after we do Raney nickel, that's going to remove the sulfurs altogether. And we just get the cyclohexane on the side of the benzene there. Questions there? All right, here we come across a synthesis problem. So we're starting with an alkene, and we are needing to add this group right here. So I'm going to show you what a student proposed, and you can tell me if it is a true or correct, and then B, if it is not correct. All right, so we have a split pool here. So if we go through the synthesis, we can see if this works. So in the first step, they're using BH3THF to add an alcohol to the less substituted position. So the synthesis step works and it gets the right product. PCC will oxidize it to the aldehyde. And then adding the NH2R double prime, where R double prime is isopropyl, will give us, so they're adding NH2 with this in the presence of catalytic acid. And in this reaction, an aldehyde with a primary amine is going to give us an imine. So this synthesis does work. This one is true. Does anybody have questions on any of the steps here? All right, and then I forgot about this one that was on here. This student, trying to follow, this might be a different problem. Oh, so this student made an epoxide using MCPBA, so this was their starting material. And then I'm not sure what that step, I think they were trying to open it up with HBr, and then to do the aldehyde here with the Br, but this is not a way to make the Br. So this synthesis over here would not work. So this step doesn't work. The PCC, if you got to this, could oxidize to the aldehyde, and then this imine would form here. And then they have to get rid of the Br, and so they're trying to use T-butoxide, and there's already a double bond there, so that wouldn't work. So this one would not be the best way to do it. This first synthesis is a good method here. Questions there? All right, on this slide, we're adding a bromine and this other weird R group over here. So you can look at the two syntheses and tell me what you think of them. We'll look at the first one first. Does it work? Yes. B, no. So let's look at the first one first. All right, so most of you that voted, 3/5 of you that voted, the majority of those said yes, this would work. And so let's go through the synthesis here. That first step, we have benzene. And to that, we're going to do a Friedel-Crafts acylation, which adds this acyl group onto the benzene ring. And the students indicated that that is a meta director, and that is true because we had this electron withdrawing carbonyl there. And so when we add the bromine, that should add to the meta position, which this one is. The only problem I have with that step here is the OR product, because it should only be a meta product. If you were going to do an OR, the bromine would be at the bottom, at the 1,3 position, and not the 2 position. So the one that's below here where the OR is, that should not be there. And once you have that acyl group, then you can do the Wittig reaction. And they've just added the CH2 double bonded to the PPH3. So that's the Wittig, and that will add that double bond there. So that one does work. How about the second one? Yes or no? All right, so most of you are chiming in with no, this will not work. And let's see which part of it doesn't work. So if we have Br2, that step works fine. And that will add. And then they're going to do a Friedel-Crafts followed by NBS and then t-butoxide. The no part of this that doesn't work is the bromine. So if you add anything to the bromine, that is an ortho para director. So we're not going to get the meta relationship here. And so with the two reagents, this would either way is going to give you the wrong director. So we do want to add that acyl group first in order to get the right directing effects here. All right, so that was the only thing wrong with that synthesis, is that the products were wrong. Going forward from here, if you actually were able to get this direction, the NBS step works, and then the T-butoxide step will also give you that product. So the only problem was the directing effects on that one. Is there any questions there? All right, so this one is asking to identify reactants for each of these imines. So this is just the one here. So can you make this imine, letter A here, using the following reagents? All right, the majority of you went with yes here, and the answer is yes. So if you're looking at the product, we know that if you're forming an imine, which this is, it came from an aldehyde and a primary amine. The carbon double bond side is where the aldehyde or ketone came from. So that's where we get this cyclopentanone from. And then the other half is going to be the amine. So we have a 6-membered ring with the nitrogen coming off of there. So cyclohexylamine. Questions on that one? All right, so this one is, what is the product if you hydrolyze this? So hydrolyze means that you're adding acid and water. So is this the products that you would get in this case? So you can look at, so the common thread here is cyclopentanone. The second student just didn't add the extra products. So is this correct? Yes or no? All right, for this one's a little bit harder to see because it is the enamine. Most of you voted for yes for this one. But the way to kind of go about this, if you're doing the backwards thought process here, is if this is an enamine, because this is not an N double bond to something, the one step back from here, you can think about it would be the N with the positive charge. And then at that point, then it's a little bit easier to see the separation there. And from there, you get the cyclopentanone which is common to both of these, plus the nitrogen and the 2 methyl groups. And that is from this part of the molecule. So these both give you the same product there. Questions there? All right, synthesis. This one we do not have submitted answers for, but we can look on a synthesis of this one. And one of the things first to notice here is that we're adding a whole bunch of stuff. And on the stuff that is added, I am observing an enamine, which we just saw. So if you're doing the retrosynthesis for that, you could think about this intermediate here, which you can then break down to this plus the H, the dimethylamine. All right, and then in order to synthesize this acetophenone, we are just adding 2 carbons with the acyl group. Hopefully you can see that in there. So we just take whatever's on that ring group there and add a chlorine to it, plus AlCl3. And then from that, we can add the dimethylamine with catalytic acid in order to get that enamine. And the double bond won't go in the direction toward the benzene ring because that would be too many bonds to carbon there. Questions there? All right, let's look at a next one. All right, in this problem, I added these ones on. These are good in-between step ones. So we're looking at figuring out what A through D is based on our starting material of cyclohexene. If we add cyclohexene, which H3O plus, which is H2O plus acid, that is going to give us an alcohol with no rearrangements. Chromic acid is the equivalent of the Jones reagent, which will oxidize. Whoops. To C double bond O. If we add NH2, NH2, and H plus, this is kind of the first half of the Wolff-Kishner. So we're going to get the N with NH2 here. And then if we add sodium hydroxide and heat, we'll just get cyclohexanone. What reagent could we use to get here in one step? Does anybody remember? So if we're going to get rid of the double bond, we can just use H2 and palladium. Questions there? All right, why don't you try to figure out what these ones are. I'll give you a couple minutes and figure out what the intermediates are and then what your final product is going to be from that. All right, so hopefully for A, you added a bromine. I can go anywhere on the ring. And the addition of magnesium metal is going to make it into a Grignard. So we insert that bromine in between the benzene and the bromine. And then we add formaldehyde to that. So this carbon here can attack here. So we're adding a carbon. And that second step of water will add the alcohol there. And PCC is going to oxidize that to the aldehyde. And then the aldehyde plus this carbon chain here, there's two alcohols, we're going to get the acetal. Any questions there? All right, so that's the problem set I had for today. Tomorrow we'll look at some synthesis problems where we actually have to use the protecting groups. So they'll come from the problem set in the problem set book in some of the chapter 20 problems, but how you can use protecting groups and why we might need to do that to do some of these reactions. So if you have questions, you can ask them now. Otherwise, I will see you tomorrow.